Welcome to qnawire.
All right. So we're talking about the van der Waals equation, right? And yeah, this is kind of a weird question because it seems to me that the answer is all of the above, and also that the very last statement, gas particles have non-zero volumes and interact with each other, is also true. So let's go through these. I mean, that's what I would suggest. 4 and 5 are both true if that's possible. But let's double check, statements 1, 2, and 3 and see if that's correct, right? Um, so, yeah, what is the van der Waals equation to begin with, right? It's essentially the ideal gas equation with some slight changes to it, right? And there's one way that it can be written that makes that particularly clear, and one way that doesn't. So let's start with the ideal gas equation, right? PV equals nRT. That's fine. And the way I like to see the van der Waals equation is that P is replaced with P plus AN squared over V squared, and that V is replaced with V minus NB, right? So then we know that there's this correspondence, right? Well, we used to have P, now we're adding something, right? And where we used to have V, now we're subtracting something, right? And then we can reason about what those changes will do, right? So, right, P is like the pressure you would measure. V is the volume you would measure. And then this is an adjustment you make that accounts for the fact that there are intermolecular attractions, right? So if two molecules are attracted to each other, they're going to exert less pressure than they would otherwise, right? They're going to group up. They're going to occupy less volume, right? If they're attracted to each other, whereas before they might have taken up this much space, all of a sudden they're going to take up this much space because they're stuck together. It's kind of like you can imagine if you had a bunch of single oxygen molecules floating around. Let's say there were 6 of them. That this would look pretty different if instead you had 6 oxygen molecules or atoms. Sorry, 6 oxygen atoms floating around. It's going to look different than 3 O2 molecules, right? That's going to occupy less space. But at the end of the day, it's still 6 oxygens, right? 6 oxygen atoms. 6 oxygen atoms. But when they're attracted to each other, it's different, okay? Not quite the same as that, but it's the same idea. Okay, so that's what this adjustment is accounting for. So is that reflected? The molecular attractions between particles of gases decreases the pressure exerted by the gas. Yes, that is true. Definitely true. Okay. What about this next statement? The non-zero volumes of gas particles effectively decrease the amount of empty space between them. Right? Okay, so that's talking about this volume term. Okay. And we're saying that there's a difference between this and this, right, in terms of gas molecules. That if you have a bunch of these, it's going to be different than having a bunch of these. Okay. And what they're saying is that this is going to decrease the amount of empty space, right, between gas molecules. And that's totally true, Right? Bigger gas molecules will have less empty space between them. So let's go to the next statement. Molar volumes of gases of different types are different. Yeah, so molar volume is simply going to be N over V, right? V over N. And yeah, this is true, right? It's the volume per mole is going to be different for a very small gas molecule and a very large one, or it's going to be different for molecules that are attracted to each other versus those that are not attracted to each other. Yeah. So all of the above statements are true. The final statement is also true. Gas particles have non-zero volumes and interact with each other. So everything in this statement is true. It's probably all of the above, and that's supposed to be at the bottom, and not second from the bottom.